Let me record on this computer. Okay. All right, it's set to record here. I'll put it up on something later. We'll figure it out. So questions till here. Everything we've covered till now about branch prediction. I assume that's means nobody has it. Everybody understood everything till now. Or more questions might come up as we go through, I guess. Okay. So let's continue. We looked at a bunch of different ways of organizing branch prediction. We looked at some simple branch prediction stuff, like just going to go through quickly. We looked at how to predict if a branch exists in a cache line. You use some kind of partial decode in the L1 cache. One way to speed that up would be to do the partial decode when you're filling in from L2. And another way to remove that entirely is to store just if a branch exists in that cache line when you first encounter that branch, right? So this trades off a little bit of accuracy by storing the fact that is there a single cache, like is there any branch at all in that cache line? And if you're willing to devote some more bits, you can actually store for each instruction in that cache line what the target would be and things like that. Then we looked at how you could store targets, branch targets. You do that using something called a structure that essentially maps from the branch instruction address to the branch target address. Then you can reduce the overhead of storage by using only a portion of the tag of the address as a tag, and also by doing PC relative indexing on the addresses that are stored, the target addresses. So with that, then we looked at how this works for calls, but not so much for returns, and why we would essentially need something like a return address stack for that to work. So with that quick recap, let's start from here. The essential hypothesis that is behind any sort of branch prediction really is that if there was if a branch was previously taken, there's a good chance it'll be taken again. An example is a for loop like this. That branch will be taken 99,999 times in a row. So if you had a simple predictor that just said taken all the time, it would be really, really good, right? Like it would be 99,999 times correct and wrong once. So how do you build such a predictor? Well, you could take a radical approach and say, hey, I'm not going to do any prediction. I'm always going to predict not taken. This is the simplest, or always predict taken. This is the simplest kind of a predictor that you can build. It's really just a latch that always says one, or you even eliminate that and say, yes, I'm going to take this. Here's the branch, right? So if you were to predict not taken all the time, you'd have no fetch bubbles. You always fetch the next line, the next instruction, but then it's going to do horribly on loops because you're never going to loop back. You're always going to start going forward, right? Now you could do the inverse, which is predict taken always, and then you do really well on loops. but horribly on if statements, right? Like, for example, if you have this, piece of code here, the p calloc num size of p, whatever, and then you're doing a safety check. Did you actually get any memory? Now, usually under normal execution, that p is never going to be null, right? Like, it's almost impossible. It's always a error condition, something that typically does not occur where you run out of memory, where you go into a state where p is null. So in that case, if you always predict taken, you're always going to go and run this error handler, which is useless, right? Like, you're never going to it's never going to be actually executed. So how do you get better than this? Anybody have ideas on what we can do to both handle loops and if statements pretty well? Can you guys hear me? Did you guys understand the question?
Well, is there a way to tell the difference between when we're in the loop and when we're in like an if statement?
Yes.
So could you run one in? Could you use one type of branch prediction when in a loop and one type when in an if statement?
You could, right? Like, how would you tell though? How would you know when is what? When you're in which case? Actually, there's a simpler one. Let's deal with the simpler way of doing this rather than going through with multiple predictors and having to predict. Yes.
Would it be that with a loop, the branch instruction would go back to a command earlier than the branch, and then if it's an if statement, it would go to a command later. So like your branch destination would be later if it's an if statement, and earlier if it's a loop.
Yes. What are you going to do with that information?
You could use that as a way for categorizing what type of branch you're doing.
Well, that's true, but there are ways to implement loops the other, like, such that you go forward by having the check at the top as well. So yeah. Well, no, okay. So the thing I was trying to, yeah.
How about if you just have different instructions?
Have a different.
Like when the compiler compiles if conditions, it uses a completely different instruction, like a different type of jump instruction. And then when it compiles for instructions, it has a different type of for instruction.
That might work. That might work. It's just that there's no, like, I don't know of any ISA that actually has that. Most of them just have, a conditional jump or a regular jump or a long jump. So, yeah. I mean, both an if and a for loop, the conditional typically is implemented with a conditional jump. It might work to have different instructions, and then you can have different prediction behavior, but I don't know of an ISA that does that. But what I was actually trying to get at is you could actually handle this with a local history predictor where you do what you did the last time, right? We'll see that in a second. It's also, typically called a last outcome predictor. The idea is, you keep track of what you did the last time and you continue to do that. Here's an example of 3 different types jumps, three different whatever conditional jumps. We're going to use these a little as a running example, so just keep track of this. So the first one, the for I equals 0, I less than 100,000, I plus plus, is at DC08, and this loop, this conditional jump is actually going to be true or taken for most of the loop, right? Only the last iteration is it goes not taken. DC44 is a check of is I divisible by 100, and this is actually going to be not taken for 1,000. It's going to be taken 1,000 times and then not taken 99,000 times, right? And the last one is, it checks whether the last bit is set. And so is it even or odd? This one is actually interestingly harder for a last outcome predictor because it's both taken and not taken alternatively. So if you had these if your loop like this, right? What would you do with the first? How would you be able to predict the first one? What kind of a hardware structure would you use to predict the taken or not taken in the first case? What information do you need to store?
Maybe, well, each instruction has a memory address location. So then for each instruction, you can store what happened the last time. And then each time you need to make a decision, you just reference that.
So what do you mean by what? How do you store that? What's the storage requirement? Like, what's the amount of data you want to use?
I guess the amount of data would just be the address, because you don't really need to. If you have the address of the instruction, then you can
need to store the address.
Is there something? Does one of the existing data structures allow us to do this?
No, do you need to store the address, right? Like if you were to design this in software, well, how would you build it? What would you use? What data structure would you use to build something that is a lookup of a single piece of information and an update of that piece of information? And your lookup identifier is the address. What would you use?
I mean, it seems like you might be talking about some type of hash structure.
Yes.
A Boolean? Oh, okay.
Yes, the storage would be a single Boolean, right? Like be a single bit actually. The stuff that you're storing in the hash table would be a single bit, and then the index to figure out where to look would be a hash of the address that you're looking at. Similar to how we were looking at this with the branch target predictor, right? So this is called a 1-bit counter. For you can even have a 1-bit counter that's global. There's no addressing lookup. You just have 1 bit, and it says the last branch I encountered, I took it, so this one I will take it as well. Predictably, that does pretty poorly. So we tend to have PC indexed counters as well, as we'll see they'll get quite complicated. How would a 1-bit counter do on DC44?
It would do pretty well because 99.9% of the time you're not going to take it.
Okay. How would it do on DC50?
like half right, half wrong?
Well,
It's gonna,
actually, sorry.
I was gonna suggest maybe it's gonna fail each and every time because each prediction it's gonna make. I mean, at one iteration it's gonna be even, the next iteration is gonna be false. So in one iteration it's gonna take the branch, whereas in the next it's not going to take it, and it's just gonna keep failing each time.
Yes, that's essentially it. So one bit predictor would fail horribly on DC50. So we'll have a look at that. For the first one, where you're predicting whether the for loop is whether you jump into it or not, you're going to have two mispredictions. One at the start, where you may get lucky and it may say taken, or it typically will say not taken because it has no value, right? It has no information. So that one, the first iteration could go either way, but let's count that as a possible failure. And then the last iteration will fail because it'll say taken, whereas you're actually not taken, right? So it's the prediction rate for 1-bit branch predictor for the first for loop branch is whatever 99.998%. The prediction rate for the second thing, where it's the is it divisible by, is it 100, right? Like, is it a multiple of 100? We'll have typically a 98%. It fails every 100. I'm assuming this. Let's go with this number. And then the last one will actually have a 0% prediction rate, which is because it predicts everything wrong, right? It says taken when it's not taken, and it says not taken when it's taken because it's using the last piece of information that it had. How do you think we can do better? How can we do better for the last one? Better than 0% prediction.
Look at the previous two.
What would that teach you?
Could like look at the previous in number of like patterns and then just like randomly choose the result based on the frequency of trues or falses. So like if 75% of the time it was true, you would just, I don't know if you can do randomness in hardware, but
so you can't really do randomness in hardware. I mean, you can, but you'll get truly random. You're not sure if you want that. You can actually store probabilities. You can compute probabilities and store them in a table and then use that. We'll look at that in a second. Right now, what I was actually hoping to get into was, I think what somebody else said, which was look at the last two. We'll come back to the, tracking probabilities of outcomes thing. So, if we were to go to a 2-bit counter instead of a 1-bit counter, so if this is a finite state machine for a 1-bit counter, where, if your last branch was not taken, you stay in, and you predicted correctly that it was not taken, you stay in not taken. If you need a prediction, you always say not taken. The first instance you have of a taken branch, you transition to taken, stay there while it loops in taken, and then transition back to not taken when you see a not taken. This works for the first two loops that we saw, the first two jumps that we saw, the for loop and the if I is equal to, if I mod 100 equals 0 case, just because their patterns are, they reach a state and they stay in that state for a while. To help improve the last case, which was the flip-flop between taken and not taken, we could do this. We could use a 2-bit counter. A 2-bit counter, you know, has the following finite state machine. You start at 0, and then if you see not taken, you stay at 0. If you see it taken, you transition to 1. But at 1, the prediction is still non-taken. It's still not taken. And if you receive a not taken output, you go back to 0. Now, if at 1 you receive a you mispredicted and the actual result was taken, you go to 2. The 2 and 3 are both states in which you will predict taken. And you can see the transitions back. So why would this do better, and how much better on the case where the loop is, the conditional is a check, or forgetting about the conditional, where the pattern is taken, not taken, taken, not taken, right? An alternating pattern. Why would this do better?
It would be wrong for the first 2, right? Because it would be not. Is it taken then not taken, or is it not taken then taken?
Let's go with not taken, taken, not taken, taken. Right.
So it would do the first one correctly, and then the second one incorrectly because it's still not taken. But then it would fall correctly until the end.
Would it go correctly all the way to the end? I mean, like what do you think the prediction rate would be for this?
Oh, no, it wouldn't. Because after the second taken, it would go to taken, 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 taken. So you would miss every third?
Every third? No, you'd essentially, okay, let's walk through this. So if we had, is there, and oh yeah. Right, so if we had not taken, oh, this is harder. So when you come to not taken, right, like if this was the pattern, let's just draw it somewhere. When you come here, it's not taken, it predicts not taken, it stays in here, right? So we'll write out prediction and we'll write out state. So the first case, it predicts not taken. So let's just say, or let's actually use whether it's correct or not. Right, so it predicts correctly. State, it goes to 1, right? Transition's over. Let's say it started at 0. Then you get to taken. Prediction is still not taken. It's wrong. And its state goes, oh, actually, no, this was still 0. Sorry, my bad. It stays in here, and then it's taken, so it goes to 1 at this point. And then it predicts not taken, so that's correct. And the actual value is not taken, so it goes back. It's now at state 0. Right? And then it predicts not taken, so this is wrong. It goes to 1. That's right. It goes to 0. Not taken, goes to 1, and so on. Does that make sense?
Yeah, I see where I misunderstood.
Yeah, okay. So it actually, the prediction rate here is 50%. Assuming, so around 50%. Yeah. So, this is better than 0, but it's still not as good as it was for the other 2 cases. And The other cases may have a minor penalty for, let's go forward. Right. So the other cases may have some minor penalties. Okay, I don't think this example is actually showing that. So it's just showing you the warm-up time for the first example. So for the for loop conditional, the initial warm-up for that for a 1-bit counter would have been, one iteration. It would be wrong the first iteration. For a 2-bit counter, it'll be wrong the first 2 times, right? It will go to, it'll have to go through 0 and then 1 and reach 2 before it starts saying taken. And then it has that behavior until the end, where the last one will fail inevitably. And so fine, that's how it is. So there's an increased overhead of 1 extra misprediction for the during the startup when you're using a 2-bit predictor. And as you increase the number of bits that you're using in the predictor, you have that many that much of an overhead when doing the prediction, right? But this can smoothly handle the case where you have one, incidentally, you have one time when it goes to not, and then comes back, not taken, and then comes back to taken. So in this case up here, when a 1-bit predictor will be wrong twice, whereas the 2-bit predictor will only be wrong once for that kind of a pattern. Yeah. So for we're going to get DC08 to 99.999%. That was the for loop. And then DC44, which was the check for 100, whether the number is a multiple of 100, now becomes a 99.99% prediction rate. Yeah. Does that make sense so far? Does anyone have any questions on what we've seen till now? Okay, I guess not. So what does this look like when you lay it out in hardware? So it looks something like this. A very simplified example of this would be you pass the PC to a hash function. That hash function, puts out some number of bits, typically log2 of n, where n is the number of counters that you have. And then inside this counter array or whatever, this counter structure, you have 2-bit counters that keep track of previous performance for that PC. Now, multiple PCs can hash to the same counter, so there's some noise, but then when you're in a tight loop, it's typically the only instruction that's actually hashing to that counter, so you're typically fine. This just allows you to reuse some of the space, not have infinitely large number of counters for when you're transitioning through the program. And then you typically have some kind of a update logic that takes the actual outcome. So if the branch was taken, you make the counter transition. If the branch was not taken, you update the counter. And yeah. So in some cases, you may need to ignore certain bits for, because you're using the log base 2 of n least significant bits of the PC. For RISC, when instructions are typically 4 bytes wide, you can ignore the lowest order bits, right? You can order 2 bits essentially, right? But you can't do that in CISC because the instructions can start anywhere. So this depends on the encoding scheme of the ISA. Now we still have only got to about 50% prediction rate for DC50, the branch that toggles on every iteration. But there's still a pattern, right? The pattern is n, like if you write this in regular expression, it's NT star, right? You can have as many of those as you want. And then there are other types of patterns that you could find as well. You could have this one where it's taken, taken, not taken, taken, not taken. And then that repeats over time. And I think somebody mentioned this earlier where he said one way to predict this is a repeating pattern like this is to use branch correlation, which is what happened the last few times, or maybe what happened with other branches. Now, in this case, we can actually look at what happened just with this one branch, what happened the last few times. So how do we do that? You have an extra bit that said what was the last outcome, right? And then maybe you need to actually store 2 counters instead of 1 counter. The 2 counters would be, if this was taken the last time, use one of them, and if it was not taken, use the other one. Right? So yeah, this is kind of how you would lay these out. For example, if prediction, if the previous outcome was taken, where 1 is taken, you would use the prediction from the counter, the second counter, which this is the 0th counter, this is the first counter, which is at 0 because it has seen not taken so many times, it's saturated to 0. Whereas if the previous outcome was 0, we would then use the first counter, which is at state 3 because it has seen taken so many times, and so it predicts taken. So you can actually get this to work with the alternating branches, right? There might be an interesting case there of if you had both counter saturating to taken when it was taken, it might be wrong, and that would just count down. Like it might be wrong once, and so the value will go down once, but then thereafter it's right, so you can deal with that that pattern. And this is for the second pattern that we looked at just now, which was, where did it go there? TT and TN, right? So if we were to write this out, so let's say we started with this pattern here. You'd get, the previous, let's say the previous was this, right? So previous was not taken, or maybe we'll start here. So the previous was taken. So previous was taken. We're now going to be looking at the taken counter. We'll say, or maybe we should start here so that it's wrong. Sorry. Previous was taken. So we will predict taken. It's not taken though. It goes down 1. Previous was not taken. So we'll look at the other counter. It says 3, says taken. This is correct. We move forward. Now the previous was taken, and this thing is going to predict taken, which is wrong. Well, I guess the pattern's different, but let's talk about this pattern that we're looking at. So this will be wrong. And given that this one has actually been wrong twice, now this will go to 1. And then we come forward, when we move forward, we come here. The previous was not taken. So we will look at this one. We'll say T, that's correct. Move forward. We come back here. Previous was taken, but this one is at 1. We'll actually get this wrong. We'll predict not taken, but we'll update that. So I guess a 2-bit counter has some error rate on this, right? It's not exactly very good at dealing with this pattern where it actually causes us to be a problem. We may need to use more bits, more previous branch history. So you could do, a deeper history. You could cover 3 previous outcomes, for example. This might help you with that TT and TN case. And in this case, you'd store 3 outcomes, and then you'd have 8 counters, 8 2-bit counters, so 16 bits. And you'd access each of these counters based on the previous outcome history. Does anyone want to try this out or I guess it's a little harder over video chat. Yeah, let's try this out for TT and maybe this works better. All right. Right, so let's assume that it was in this state, whatever is given here. So the last outcomes was 001, which means that we access this bit. So it says taken. So we're right, that thing stays in taken. Okay. So now the this thing will be 011. That would be this one. And that says not taken. So this would be wrong. And this would update to 1. Right. And now we're at taken, 111, which would be here. And that would actually say taken, which is wrong. So we're going to predict this wrong. But we're going to switch this to 1. So taken, not taken, 110, which would be this one. And it would say taken, stays the same. 101. Four, and then 1, right. So this one would come down to 0, be wrong, and so on. Anyway, you guys get the point. So right now at this point it's doing not so great, but as it goes through, it might get these values into a better shape and do better. or maybe not. Right? It's just a heuristic process, and so you're hoping that it works well for certain states. There may be a better way of doing this, which we'll see in a second. Anyway, questions on 2-bit counters and 1-bit counters till now?
I'm starting to wonder, we're adding all this additional machinery on top for branch prediction. How many cycles does it take to actually do this prediction versus how long it would take to just wait for the actual value?
Okay, we will see that in a second. So the schemes that we've seen till now are like overly simplistic. We will see how we can actually modify them such that they're realizable, right? So that's a nice segue into how you'd organize predictors. So you could have a couple of different things where you have the you have the history stored with a bunch of predictors. So there's a different pattern for each branch. You could have it such that you hash into some set of patterns, and then those patterns tell you which predictor to look at. Or you could have a mix of both, which is that this tells you a set of patterns to look at, but then you're restricted to look at a smaller set of predictors. So you're not, in this case, all the patterns and all the predictors are shared across all of the branches in the program, whereas here it's restricted to some smaller set, right? So in this case, this would be the least amount of hardware implementation, and it would typically be quite fast because it's a hash operation which depending on how you implement it might be as simple as masking a couple of bits out, and then a lookup or the cam, which shouldn't take too long. It's like a register read, so you can have a cycle, and then a lookup on a bunch of bits again, which can be implemented as a register or a cam. And so most of this should fit into a single cycle without extending the cycle too much, obviously. So yeah, we'll see more examples of how you do this mix of both, which typically tends to give you which typically is a generalization of both cases, right? Like this is one extreme, this is the other extreme, this is somewhere in between of both of those. So let's assume that you had 1024 counters, 2-part-10 counters. You could split it in a couple of ways. One way that we're looking at here is if you used a 5-bit PC hash to choose a set, right? So you use 5 bits of the PC to choose a set, and then within that set, there are 32 counters, 2-part-5, 5 bits, and so you're using a history length of 5, right? Now the disadvantage of this, of course, is that you have thousands of branches collapsed into only 32 sets. So you'll have a lot of branch collisions. You can go the other way, where you go to 128 sets, so 7 bits are used to choose a set, but now you only have about a history length of 3, right? You only have 3 bits left in the 2-part-10. So you can have about a history length of 3. Now, you've gone the other direction. Now you have a problem of history length. You can also do the mixed, right? So these were examples where you had dedicated sets. And you could also do the 2-level style where you're looking at history that's kind of shared, and then a set of branch predictors that are kind of shared. And both of these will be obtained by using different parts of the PC address. So some portion A is going to be used to hash into the branch history table. And then some portion of the address B is going to be used to offset into the pattern history table, right? So in here you have 2-bar A sets with H-bit history. And then you have 2-bar B sets down here with about 2-bar H counters per set, H being the length of history that you chose to store in the branch history table. So the total size of this table is going to be H into 2-bar A, right? So you have H bits, 2-bar A entries, plus 2-bar B plus H into 2. Because each entry is a 2-bit counter. That's where this 2-bar, this into 2 comes from. And this, can be, you can choose how to design this in a couple of different ways. You can have H and RA equals 0. So then just becomes a regular table of 2-bit counters. You can have H greater than 0 and A greater than 0. That will give you local history. So this predicts branches from its own previous outcomes. And you can have H greater than 0 and A equal to 0. This gives you global history. So it predicts branches from previous outcomes of all branches, if that makes sense. Right, so just to make that clearer, if you set this to 0, if A were equal to 0, there's only one set of there's only one entry in the branch history table, so you can have an H, but that will capture all global branches that you've seen. You can have A greater than 0, and then you have local history, some case, some definition of local, right? Like you're hashing a bunch of things into there. So interestingly, the global predictor may even do well. Reason for something like that is, you have things like related branch conditions, right? Like, so if you had this code where it's P equals find node foo, and if P is parent, you have branch, A do something, and then you have some stuff that, does other things, and then if P is child, do something else, right? The outcomes of these branches A and B are always the opposite of the of each other. So if the first branch is taken, the second branch is always not taken. So there's a global correlation because these two are different PCs, but they're gonna, they're dependent on each other, right? So this is kind of like an if else, although this is written as if. And so it might make sense to actually build a branch history register, a global history predictor, and a local history predictor. So the idea here is that we take a branch history predictor, a branch history register, which is, the single entry branch history table would be called branch history register. This is global history. And then you can use the B portion of the PC hash, put that together with the branch history that gives you a offset into the pattern table, and then you can go check that counter, and that will tell you what should happen next. again, there's a trade-off here between B and H. The larger the H, smaller the B, which means you have longer history, longer global history, able to capture more patterns, and longer warm-up time. But if you have smaller B, there are more branches. Because you have smaller B, you have more branches mapping to the same set of counters, so you have more interference. Larger B, smaller H, just the opposite. You have smaller, you have shorter history, but you have less interference, if that makes sense. Yeah, does that make sense to people? Questions? Okay, I guess not. So I'm actually going to skip combined indexing. Right. And I come here, which is we're looking at an issue where you have, global history helps certain branches, and then global history hurts certain branches, right? Like, so local history is the one that you want for certain branches. So examples would be local history, loop branch. It would be a loop, right? Where your future outcomes are dependent on your previous outcomes of the same instruction. Whereas with global history, that works well for things like if else, else if, that kind of a branching pattern where it's just a tree of ifs and else, because they all kind of depend on each other. But then they tend to be often, they tend to not work when you use the other case. So if you had global history for a loop branch, that would not work so well because it's useless information. And then local history tends to not be a correct indicator of an if-else tree, because if you were to look at the previous outcome for an else statement, it may not have been taken, but in this run, it may need to be taken because the if statement was not taken, right? So they kind of are useless in each other's cases. So how do we deal with that? And this kind of comes to something that somebody had brought up both last class and this class. Someone want to take a guess? I mean, somebody actually mentioned this earlier in the class. Like, what would you do in a case where you have two different things? We were talking about fors and ifs, and somebody said, why do we choose between the two? Does someone want to take a guess at how you do that?
Mm-hmm.
Do you understand the question?
Could you repeat?
Sure. What happens, like we've seen how you build a local history predictor and a global history predictor, right? And they both work well for different types of branches. For loops, a local history works well, or for a while loop, whatever. For a if else kind of statement, global history works well. But building both, if you only have one type of, if you choose to build local history, or you choose to build global history, you're going to hurt the cases that benefit from the other one. So how would you get over that? How would you, figure out which one to use when? Let's say you built both. Well, how would you figure out which one to use when?
When it just
Have
depends. You go. Who was speaking? Okay. Wouldn't it depend on the like the type of loop with what type of variables you'd be, the type of loop and not variables, the arguments as to what the condition is and what kind of predictor you should be building. That's still extremely vague, but
Yes, that is essentially what I was saying. Right. Okay. Let me just talk to you guys. So essentially, because you're trying to predict you're trying to figure out which which predictor to use, the global history or the local history. You can actually build out both types of predictors. They may be using the same history tables and all of that, just have slightly different control logic. And then you have a meta predictor, right? It could be essentially something that's indexed with the PC for that particular address, and then you pass the PCs to all of them. And then you get two predictions, and you get a meta prediction, which is which of these predictors do I go with. And it could be a simple 2-bit counter, which says, starts with always take the local history, and then kind of as it saturates the other direction, because you keep making a mistake for the if-else, says, oh no, use the global history predictor, and so on. And so in this way, you kind of have built a tournament predictor, which is, goes between the two based on which one performs better. But all of this is indexed by the PC. That makes sense? So, predictably, if you have longer branch histories, you have more context. You can make decisions better, but then, it also increases the prediction history table exponentially, because you always have order 2 power h counters, 2 power b plus h, but it's order 2 power h counters. And training time increases, possibly decreasing accuracy if you have small branch predictions. So, just to see predictor training time, you have, if you had a history length of 2, you need to train it, whatever. There are 4 states to go through to train. And, if you had 3, it probably takes about 3 or 4 tries before you get into the right state. And, the last case, I guess the obvious case is, we've dealt with this, branch prediction can go wrong. That's one of the reasons why we're able to make any trade-offs that we want between accuracy and space. And, what do we do when you get it wrong? You correct fetch, go to the correct address. You hunt down and squash instructions on the wrong path, right? So how would this look in the pipeline? So, if this was a 4-white superscalar, so you fetch the branch, you put it in. You have the in decode you have the branch, and you fetched A, right? The next instruction. You dispatch the branch to this one, and A goes on. At this point, you detect that you've mispredicted the branch, right? You shouldn't have loaded A, you should have loaded something else. So then all of these blocks, could have been, and then remember there are 4 blocks here that we're not showing what's in them, but because each thing is a 4-byte superscalar, each of these could have 4 operations in them. They might be, you have to go and squash all of those operations that could be in flight. So yeah, what would you do in each case? If you in the fetch, you're typically predicting the things here, so you don't really know if you've made a mistake in fetch. So that's just how it is. In instruction decode, you can tell whether the branch is a return or an indirect jump or a phantom branch. We'll see what phantom branches are in a second. If it is a return, the target that was predicted is probably wrong, as we saw earlier. So you go and access the return address stack and squash the branch prediction and look up and re-steer the fetch to this return address, right? Same thing with an indirect jump. If you know if you have an indirect jumps branch table buffer, use that re-steer fetch. But because we caught them in decode, we will not actually issue those instructions, so we're good. But if we caught it in dispatch, then you could have to read the instructions. Well, the thing that you would recognize in dispatch is if it was an indirect jump, and so you had to read a value from the register, and the value you read did not match what was given by the IBDB, right? If those 2 values don't match, then you have to correct the fetch and instruction decode and the L1 instruction, and then re-steer the rest of the pipeline to use the right target from the RF, right, from the register file. And that's if you detect the wrong, that you made a misprediction at the dispatch stage. This is where you would access the register file. If you were to detect it went in the wrong direction or wrong target, during the execute stage, you have to squash everything essentially, and then calculate the right PC and go into the right, steer the fetch to the right PC. Yeah. That makes sense? Does that fit back into what people understand about instruction execution in an out-of-order code? Yes. Okay. So there was something called phantom branches that I said we'll talk about later. A phantom branch is one that essentially pops up because this essentially happens because you're coalescing, because of a branch collision, right? Like you're taking a set of branches and then mapping them onto a smaller set. So you may accidentally say, given a particular cache line, there's a branch at C, whereas the actual instruction may have been, there was no branch at C, there's an XOR instead. And so it predicted, your table predicted that C was a branch, and it was taken, and then it went to X. So you start fetching A, B, C, X, whereas later you discover that, C is not, this is in the decode stage, you discover that C is not a branch, it's an XOR, that you actually need to go reroute that back to D, and then use the value Z that comes from D and move forward. This, happens because you have a collision in the branch space. So these are called phantom branches. They're typically detected in the decode, and then you re-steer it. But yeah, it's a side effect of, it's a trade-off, right? It's a side effect of the trade-off. So what does this all put together kind of look like? It's, here you have it in its gory detail. This is, the fetch side of things. This is instruction decode. So fetch is happening here, where you send the, you have a PC, goes to the L1I, the branch predictor, the branch target buffer, and this adder for the next instruction, right? Now, both these two values, the branch target buffer output and the size of the next instruction, whatever, go down to a muxer, which is then, key picked between using the branch predictor. That will give you the new PC to go with. The new PC also has the feedback from the rest, the back ends of the pipeline, so it can actually go to the right place if the prediction was wrong, but you have a new entry quickly, right? So you load the instruction, you send it to decode. You may know the actual target if it's an immediate target, or if it is an unconditional branch or not a branch, whatever. You have a bunch of things that you find out from the instruction based on the decode, which kind of feeds into control logic. And in some of these cases, there's actually there may actually be a need to re-update the PC to re-steer the fetch so that it goes the right direction. Two of these examples are, when the instruction is a return, in which case you pop. So you push onto the register stack when it's a call instruction, you pop on a return instruction, you use that to send it to send that PC to the fetch. And the same for an indirect branch, which uses the IBTB. Both of these will, feed their output to a muxer, and then the control, which uses these signals, right, that come from is indirect, is return, etc., to figure out if any of these is valid and should be piped forward. If you just find out at execute time or dispatch or whatever, there'll be other lines that come back to the next PC. Yeah.
So, quick question. As this relates to pipelining, I'm guessing, given that there is some cost associated with flushing the pipeline if you make a misprediction, and the architecture, then you can know what percentage of the time you have to be correct for branch prediction to even be beneficial, or rather even break even, let alone beneficial, right?
Yes, you can calculate that theoretically. I think, let me see if that's actually in one of these slides, or was it a different set of slides?
And then what would that number be, ballpark?
So one second, let me just see if it's there in these slides. If not, we'll look it up. It's not here. So I'm actually going to cut the rest off. I'm not going to go through the rest of these slides. So we'll stop with this one. Let me go look at whether I can find some number. My understanding is it's typically on the order of 60% is when effective. Let's see. So I can tell you the opposite statistic, which is when you drop from 99% to even 95% prediction rate, your performance drops like crazy. But what is the effectiveness of a branch predictor? Maybe something to look up, and I'll let you know next class. I don't think it's not like popping out at me. Yeah. Yep. I'll look that up and I'll let you guys know later. All right, other questions? No one has any questions? How's this lecture format working?
I think it's good.
Okay, that's one person. Anyone else have any comments? Does anybody not like this format?
I think it's good, but I do find myself I think if you could maybe break up the sections a little more clearly, that would be helpful, because I think I'm struggling to kind of see when we're moving from one to another.
Right.
So that might be helpful too.
Okay. All right. Okay. If nobody else has any other questions, I'll be around here if somebody wants to ask questions more, one-on-one.
Question.
Yeah.
Well, it's not mine. I just saw it on Piazza, but it made me wonder too. They were asking about like the final and like how is the final going to work now that we're quarantined and stuff.
So the guidelines that I've got from the university is to use Sakai. I have no idea what that is, and I've never seen it. But maybe that, or maybe we'll write up some web-based thing. I don't know, something. We'll figure something out. It's mostly going to be. It's going to be around the same date, May 4th, whatever, at the same time, and it's going to be online. It's going to be virtual. So it will be open book because there's no point in. There's no way to enforce non-open book anyway. So it's going to be an open book exam, virtual on the same day. Yeah, that's all I know till now. All right, we're gonna stop here. We'll stop the class, and yeah, I am. Whoever wants to ask any questions, I'll be here. If not, feel free to drop off.